We only have one shot. Once it goes out on the pad, we set everything up, we fuel the rocket, and we hit that button, and it has to work. You have to know what your system is going to do. We have to constantly test. Determine our reliability of all the components and subcomponents and subsystems and the systems operating within each other. Make certain that not only are our astronauts safe, but we're also going to get a rocket that performs exactly what we intended for it to do. Testing is the only way to know what exactly the rocket's going to do before it does it.
My name is Sarah Heisent. I am a manager over the energetic materials and processes at ATK Launch Systems. Energetic materials are materials that retain a lot of energy, and upon a certain stimuli, they release an abundant amount of energy in a very short amount of time. We work on both the development and the production support of a variety of energetic materials, including the Ares propellant.
Solid rocket propellant, you can compare it to the texture of a pink eraser. When we say solid, it's not quite fully solid, but you can bend and shape it and form it a little bit.
Our role is to ensure that we have reproducible propellant and one that we can depend on every flight, that we always know how it's going to perform. When you see the space shuttle or in an Ares diagram, you see the motors vertically. We test them horizontally. We have a very thick concrete wall up at the front end where the nose of the rocket is. It's bolted in and it lays horizontally on top of another concrete pad. There are all kinds of sensors and gauges along it. We're trying to get information on pressure, strain, temperature. While it's testing, you see all of the light and heat and products, gas products that are coming out extremely fast. It's quite a dramatic scene. After a rocket testing, we look at both the data that we got off those sensors and gauges, but then we also do visual inspections. We'll look at the erosion of the nozzle. We'll look at the state of the case and the insulation.
Did we have enough insulation? Did it start to burn and erode, how we predicted? We actually can go look at that and see how well it performed.
We're using liquid oxygen and liquid hydrogen on our upper stage. Liquid oxygen is roughly minus 320 degrees Fahrenheit. Liquid hydrogen is roughly minus 450 degrees. So those two fluids are extremely cold. Those flow out of the tanks through our fuel pipes into the engine where they get combined and ignited, and the exhaust is coming out at positive 4,000 degrees Fahrenheit. That's a tremendous temperature difference. And all of those components have to be designed and tested to make sure they're going to survive that environment. Another aspect is vibration. We're going to put a fully assembled Ares launch vehicle and test it and see how much vibration or how flexible that launch vehicle is.
My name is Kathy Owen, and I work here at NASA's Marshall Space Flight Center in Huntsville, Alabama. I've been a test engineer at the Marshall Space Flight Center for about 20 years now. This is the top of the dynamic test stand. This test stand was built back in the 1960s for the Saturn V test program. And then it was also used in the late 1970s for the shuttle dynamic test program. We're preparing this facility now to test the Ares 1 rocket. This is the ground floor of the dynamic test stand, and this is where the bottom of the Ares 1 vehicle will be. We will stack the first stage hardware, then we'll get our upper stage hardware, stack it on top of the first stage. Then we'll stack the Orion hardware, and that includes the crew module and the launch abort system. When the total launch vehicle is stacked in here, it's about 327 feet tall, so it will come nearly to the roof of the building. This will be the first location that the Ares 1 rocket will be stacked, and we will learn about how it vibrates, and that way we can be sure that our models are correct.
Launch vehicles are quite flexible. Most of the thrust is going to go straight up the axis of the launch vehicle, but then it's going to have a tendency to want to bend, and then it's going to come back and forth. So what we're doing in the dynamic test stand is understanding how much motion this vehicle may see during its flight to be able to understand that so that we don't overcorrect for those vibrations.
You know, we got to make sure that we build it right so that when it's actually launching and that power and thrust that you feel doesn't shake your rocket apart.
I use everything that I learned in high school. I use all the maths, algebra, geometry, trigonometry, my pre-calculus. I use the sciences, physics, chemistry.
There are days where you're busy with your hands. There are days where you're looking at analysis, doing data analysis on a computer.
The other thing is you ask why a lot. You're curious. You want to investigate things and make things better and understand how they work and get data and analyze why it works. I feel like I'm a part of something bigger. I feel like I'm supporting something that I truly believe in, which is standing on the horizon, if you will, and we're pushing the envelope to not only go to the moon but go on to Mars. And I feel like I'm contributing to that and promoting human exploration and taking humans to the next level.